The three main components of Group 23's project include a ChipWhisper CW1200 scope, a CW308 capture board shown in red, the corresponding target board shown in blue, and of course the necessary cabling to support communication between the scope, the capture board, and also programming the FPGA. In this case, that is our target board. The scope is responsible for capturing the power traces from the capture board. The capture board itself typically is responsible for sending data to the target board and capturing the necessary power traces. The power traces are sent back to the scope via this analog cable here, and then the scope sends back the power traces via USB to the PC. Now the target board itself is a Spartan 6 LX9. It was chosen because it supports our circuit of interest, in this case a benchmarking or a NISCAS benchmark circuit. After successfully compiling and synthesizing the benchmark design, the bit file is sent via JTAG, in this case the JTAG is right here, using a Digilent HS2 cable. When it's sent to the FPGA, the red LED turns off, and we now know that we can successfully start capturing power traces on the target board. So next, to get our circuit up and running, we essentially need to run three pieces of software suites. So first one is the ChipWhisper server. Now the ChipWhisper server runs in the background on your local machine, and that allows you to connect to a server on the local host. And this server runs what's known as the Jupyter software. The Jupyter software allows us to run essentially Python code and communicate with both the ChipWhisper scope and the ChipWhisper capture board. So this is where we're sending all our commands in terms of setting up the scope, setting up the sort of clock rates on the scope and the capture board, sending over the required inputs. Typically those inputs would be key text pair in the case of a standard AES core, but we're not using an AES core here, so we're going to be using a different method to send inputs to our benchmark circuit. So this is Jupyter server running right now, and we have what's essentially the startup scripts for the scope. The second piece of software that we need is actually running in a virtual machine, and that's Xilinx's ISE Project Navigator. So there's a couple components to this Project Navigator. There's the actual HDL or Verilog VHDL editing software that we see here. So we have three components here. First, we have our circuit VHDL code. So this is the 6288 multiplier, and I'll show that in a second, what it sort of looks like conceptually. We have our Trojan code, or Trojan VHDL code, or rather Verilog code. And we also have code for our ROM, which feeds inputs to the multiplier. After successfully compiling the code and synthesizing it, we can send over the generated bit file to our target FPGA, in this case the Spartan 6. Now that's done through JTAG and through another piece of software called ISE Impact. So it takes that bit file and sends it over to the FPGA, and now our FPGA is successfully programmed, and we start capturing power traces. However, before we start capturing the power traces, I just want to illustrate what the actual circuit, the ISCAS85 benchmark circuit, looks like with the specific Trojan that we have chosen. So at the very top here, this is our Trojan, and the Trojan is composed of two components. We have the trigger, and we also have the payload part, which is essentially just a mux. Now this Trojan attaches to a half adder circuit shown here with A and B sums, or rather A and B inputs and a sum output. Now the half adder Trojan, we've decided to infect the very last half adder of the 6288 ISCAS benchmark. So in this circuit, you essentially have a 16-bit input and another 16-bit input that multiply each other to get a 32-bit output. So conceptually, it's made up of full adders and half adders in this sort of array here, where your products, your bits of the product start from 0 all the way up to 31. So you essentially have a 32-bit output. We've decided to infect the very last half adder circuit at the very bottom here. This should generate a bit flip when a certain condition is met. In this case, the condition flips a 0 to a 1 or 1 to a 0 when the inputs to the payload are 1 and 1. So to demonstrate what this looks like on our actual circuit, we'll be using Intel Quartus's RTL viewer. So we've been programming and we've been developing the code with Xilinx's IC Impact, but the RTL viewer on Quartus gives a nice view of what we want to see when we're looking at our circuit. So here we have our ROM, and the ROM allows us to bypass ChipWhisper's limitations around sending arbitrary inputs to our circuit. Typically, ChipWhisper only supports sending a key text pair because the ChipWhisper is usually used to attack and monitor and capture power traces of standard AES cores, of typical encryption cores. But in this case, we do not want to focus on encryption core. We want to focus on our own ISCAS85 benchmark that's been infected. So in order to send inputs to our infected circuit, we have to get around that limitation by creating a ROM. Now this ROM decouples our design away from the simple serial communication protocol that's used by ChipWhisper, which only really works with a key and text pair. Now with this ROM, we essentially go through preset values in the ROM. There's a total of 8 values. Those 8 values are both sent, and those are 16-bit values each, are sent to the multiplier, and the multiplier will start multiplying and we'll be able to capture the power traces of that active multiplication. Now to give a good view of what that infected ISCAS85 benchmark circuit looks like, we'll first open our multiplier, and the multiplier itself is comprised with over 500 plus gates here that we can see. Now we're not going to go into too much details here, but we can actually find our Trojan instance, select that, and we see that the Trojan instance is a very small portion here in red. And we can actually zoom into that instance and get a view of the Trojan. Now this is, like I said, the half adder Trojan that attaches to the very last half adder that outputs the 16th bit of the overall 32-bit output. After successfully compiling and synthesizing the design and uploading the bit file to our FPGA target, we can actually start capturing the power traces of active multiplication. In this case, we go back to our ChipWhisper software suite, and this is where we can capture the power trace, dump the power traces in an Excel file, and generate the necessary plots to determine how a clean circuit and how an infected circuit differ in their power. In this case, we have an example Excel sheet showing our data dump and showing a very sort of simple power output of the clean versus infected circuit.